If you haven't already changed your name, if you could go up and change your name to your school name and then your initials, please. If you have questions along the way, if you want to throw those questions in the chat box, then as we go along, I'll be able to answer them. And a lot of y'all were helpful last week answering questions. So if you think you know the answer, feel free to do that as well. All right. So trying to be respectful of your time, we'll go ahead and get going. And we'll go ahead and start. So Unit 2 is all about molecular bonding, ionic bonding, metallic bonding. So the three types of bonding that are out there in the world, right? So a lot of this you learned in general chem or pre-AP or honors chem. And then some of this may have been added in AP, but Unit 2 is actually a pretty easy unit. There's not a lot of math, and it's stuff that you've seen before. So we'll kind of go along. So if you haven't joined the Pear Deck, go ahead and join that now. Join pd.com and RTZGPN, and then you'll get a chance to play a part in what we're doing tonight. So here's your first question. So you get to choose an option. Which choice best differentiates ionic bonds from covalent bonds? Make sure you read each answer choice. But which choice best differentiates ionic bonds from covalent bonds? Make sure you read all the choices. Got 26 responses so far. There's 57 of y'all on here, so keep going. This is not a question from the AP exam. This is one I wrote, but it's trying to be like the AP exam, and notice that it's kind of a lot of reading, and it requires you to read all 4 answer choices. So as we get closer and closer to May and taking the AP exam, I want part of our time together as we review these things to be thinking about how can you be successful on the AP exam, and that means reading the answer responses and not just clicking on the one that maybe sounds good. So I'll give y'all like another 10 seconds to see how we're doing. And let's see what our responses are. Okay, I've got a D, a bunch of B's, an A and a C, and a couple of people who just changed their answers. That's fine. So what I wanted to do was reintroduce y'all to the concept of sometimes it's not about what the answer is, sometimes it's about what the answer ain't. So we'll kind of go through and talk about what the answers aren't, and by doing that, we'll talk about what the answer really is. So first of all, the answer can't be D, because D just sounds like it has nothing to do with bonding. Ionic bonds involve repulsion of electron domains, while covalent bonds involve attraction of electron domains. But we know electrons are negative, and so it's not like electrons can attract each other. So that one's out, right? C sounds reasonable. Ionic bonds involve atoms with greatly differing electronegativities, while covalent bonds involve atoms with the same electronegativity. So everything in that answer sounds pretty good, except for the word same. If you have the same electronegativity, then you would have to be the same element, right? So you can have a covalent bond even with different electronegativities. When things are different electronegativity-wise, they're polar. And then when they're really different, we say they're so polar that they've almost become ionic, right? And A sounds like it could be the right answer, but A is exactly the opposite of what the definition is. So covalent bonds involve sharing of electrons, involve giving and taking of electrons. So when things form ions, they either give away electrons or receive electrons. So that makes B the correct answer there. So here's another question for you. Look on the periodic table, and based on where the elements are on the periodic table, which of the following is the most ionic? Which one of those compounds is the most ionic? All right, I got 35 answers so far. Let's give y'all another 10 seconds or so. Which one is the most ionic out of all of those? The other thing to keep in mind about Pear Deck is no one knows what the answer is, right? So, I mean, no one knows what your answer was except for you. So if Bethany says, oh, the answer is D on Pear Deck, I have no idea that it's Bethany's answer, right? So just keep in mind, I have no idea who answered what. Let's see what y'all thought. Right, so most of y'all are saying E. That's good. Most of y'all are saying E, and that's a pretty reasonable response. And this is an actual AP question. So remember that ionic things are metals and nonmetals, and covalent things tend to be nonmetals. And then of course metallic things would be two metals. So if you looked on the periodic table, the first four are all nonmetals paired together with other nonmetals. All right, let's keep going. So when we talk about polarity of bonds, we're talking about electronegativity difference. So based on what you know about electronegativity, and remember that's a periodic trend that you learned in Unit 1, which one is the least polar? So the closer the electronegativity values are, then the less polar it will be. The greater the electronegativity difference, the more polar it will be. So based on your knowledge of looking at the periodic table, which one is going to be the least polar? If you know your electronegativity trend, you ought to be able to answer this question, and you can just drag the icon to the one that you think is the right answer. EP from Oxford, basically, it's not based on Coulombic attraction. Basically, it's based on electronegativity difference. So when something is more ionic, it means there's a greater difference in electronegativity values. And that also it means that it's like more polar, right? So Coulombic attractions would be talking not about the more ionic, it would be talking about the attraction for the two ions, say melting point or something like that. So let's see what y'all's answer is. Okay, y'all are dragging it a little bit everywhere. Looks like a lot of C's. Okay. Some of y'all dragged it on top of the bear. Okay. That's a choice. So which one is the least polar bond is the one that's going to be the closest in electronegativity value. So remember, fluorine is the most electronegative element on the periodic table. And the second most electronegative would be oxygen. Now, you don't have numbers on the periodic table for electronegativity values, but oxygen and fluorine should be really close in electronegativity value. So we would expect it to have the least difference and therefore be the least polar. Everything else is N and H, F and H, I and F, and those things are things that are really far apart on the periodic table. All right, so all this in terms of attraction for each other is based on Coulombs law. So if your covalent bond then you're the protons in the nucleus attracting the electrons that are being shared. So it's still Coulombs law. If you're an ionic bond, then it's the fact that an ion has a charge and it's attracting the the otherly charged particles. So if you're a sodium, you're attracting the chlorine. And all of that comes down to Coulombs law. So just one more time, Coulombs law is Q1, Q2 over R squared. Now, don't worry about the everything and the K and the squared. The Q1 and Q2 are the charge. So the greater the charge, the greater the force of attraction. And the R squared is the radius. So the bigger the radius between two ions, then the less the force of attraction. So this all ties back into those periodic trends that we talked about last week. Knowing your trends behind ionization energy and ionic radius and atomic radius will help you understand bonding and will also help you understand intermolecular forces, which is Unit 3 next week. So got to keep in mind this idea of Coulomb's law and how it affects the attraction between two things. All right, so here's a question. This is from an old AP exam. So what I want you to do when you draw through things is I want you to draw through any answer that you think is wrong. So at least one of them is right, but it could be that Roman numeral 1 and 2 are right, or 2 and 3 are right, or all three are right, right? So all those are possibilities, but if you think one of them is wrong, if you could just draw on the slide and just draw through the wrong answer. All right, so I got 43 answers. I'm just going to start peeking through them and see what I see. So this person gave me a smiley face. I marked through the third choice, marked through the third choice. This one marked through the second choice. Oh, that's lovely. Somebody gave me a blue line with many colored dots through the third one. There's a squid or a space alien or something. I'm not sure what that is. Somebody said hi. Very good. I can see some of y'all are writing with your fingers and some of y'all are writing with a mouse. Because anytime you try and draw with a mouse, I always just muck it up. Mess it up big time. Okay, now y'all are, a bunch of y'all are giving me smiley faces, which is great. I love the smiley faces. I'm gonna run down to the bottom of the list real quick. There's 74 of y'all. It's gonna take forever if we look at all of them. Okay, somebody marked through the first one. Okay. All right, so far so good. So let's go back to Coulomb's law one more time. Q1, Q2. So for a greater force of attraction, you don't want a charge of +1 and -1. For a bigger force of attraction, you want a charge of +2 or +3. Right? And Q2 of -2 or -3. The bigger the charge, the greater the force of attraction. So if we look at this question, MgO is higher than NaF. They said that as a fact. We'll believe them. Why is that a good, what's a good explanation for the observation? Well, law, you want a greater charge. So Mg has a charge of +2, Na has a charge of +1. So Roman numeral 1 checks out. That sounds fine. O2 does have a greater negative charge than F minus. So that is also true. You want a bigger charge to have a greater force of attraction. And then the last one is the last one. Does that make sense? The O2 ion, F minus ion. Well, if the O2 ion is smaller, then that would give it a greater melting point because smaller radius in the bottom of the mathematical expression means you get a greater force of attraction. So is it true that O2 minus is smaller than F minus? No, because we learned last week when we were talking about periodic trends that when two things are on the same row and they have the same number of layers of electrons, it really becomes about who has more protons pulling on those electrons. And it turns out the fluoride ion is actually going to be slightly smaller just because the fluoride ion has more protons pulling on the electrons. So Roman numeral 1 and Roman numeral 2 are correct. 3 is not. All right, so you have seen this diagram at some point in chemistry. Which one of these diagrams, A, B, C, or D, is the right diagram to explain what happens to the potential energy of two particles as they get closer and closer together? So internuclear separation in the x-axis means how far apart are they? So at the far right of the graph, that means the particles are really far apart. And at the far left of the graph, the particles are really close together. I'm just interested to think which one of those do you think is right for two atoms getting close to each other? All right, so let's see what y'all think for an answer so far. Okay, I'm getting a lot of D's, some A's and B's and C's. Okay, so this is actually from the AP exam. So let's look at what this, it's called a Morse diagram, but let's look at a Morse diagram for what's happening. At the far right-hand side of the graph, when two atoms are really far apart, there's not as great a force of attraction because they're really far apart, right? So when two things get closer and closer together, there's, but then if you look at the far left-hand side, those two hydrogens are right up on each other, and they actually get so close together that the protons start to repel each other and the electrons start to repel. So this is the same thing that you've had in your life. You walk up to somebody on the far right, you walk up to somebody, you get close, and then at some magical point, both you and the other person know that this is the correct distance that you should stand apart and talk to each other. Granted, this is pre-COVID, right? Right? So if they get to some happy point, that's great. That would be where R is equal to 74 on the graph. But if you've ever had somebody get up in your face and be like a close talker where they get right up on you and try to talk to you and you back up, they're like, hey, back up there. That's what's going on where the R is equal to 45. There's actually a force of repulsion. So at the far right-hand side of the graph, the attraction is greater than the repulsion. At the far left-hand side, repulsion is greater than the attraction. And then at that sweet spot there at the bottom of the dip, so where R is equal to 74, we call that the bond length or bond distance. And that's the point where when those two things form together, that drop in energy from 0 down to negative 432, that represents the energy that's being released. So that 432 is kind of that's the energy released as the bond forms. So whenever you look at one of these things, you're looking for that low spot, and that's the spot where attraction is equal to repulsion. So they're not being pushed together anymore, they're not being pushed apart anymore, they kind of hit that happy point right there. And the amount that you go down is equal to the bond energy, and that distance that you're measuring in the x-axis, that gives you the bond length. Questions. Don't, when two particles come close enough together, don't they just bounce off each other? Correct. As they approach each other, they would, those electron clouds will tend to interfere. And y'all have obviously been listening when your teacher talks about kinetics, and that's great. So assuming that they're coming close enough together to actually bond, and thank you, Hunter, to point that out to everybody. That's about kinetics, which is a great thing to know, but remember, I'm trying to review unit 2, right? But that's great that y'all have that knowledge. All right, so what I want you to do is I want you to put the red triangle where repulsion is greater than attraction, the green triangle where attraction is equal to repulsion, and the blue triangle in some part of the graph where attraction is greater than repulsion. So blue, where attraction is greater than repulsion at that point. Green means where the two are equal. And then red is where there's more repulsion than there is attraction. All right, let's see what y'all's answers are. Woo! Whenever there's 74 people on here, it gets a lot harder to see these. It looks like some weird painting, right? So y'all are by and large pretty good. Just remember that the closer two things get to each other, the closer somebody gets to your face, the more you're going to be repelled by them, unless they're really good looking. Maybe you want to kiss them or something. But when somebody gets right up in your face, you tend to back off because you're slightly like, no, don't invade personal space. So the red should have gone to the left of the X somewhere. The green should have gone right on the X where the two match up. And then the blue could be anywhere to the right of the X. All right, let's keep going. The other type of bonding, and I'm not going to go into this crazy because there's very few questions on the AP exam, but you should know about metallic bonding. So metallic bonds are when there's just a bunch of metals together. And remember, metals all want to lose electrons. So it's like a bunch of Girl Scouts all standing around trying to sell each other cookies. Like no one's making any headway. Just like all the metals kind of want to get rid of these electrons. So in a metallic bond, you really have this sea of electrons that surround the metallic nuclei. And that sea of electrons are highly mobile. Since no one is really pulling on them super hard, since those electrons aren't being like, oh, they're mine or anything like that. Those electrons are mobile or movable. And so the idea is those electrons can actually flow. And when electrons flow, we call that, when electrons flow, we call that conductivity, sorry. So metals are conductive because of those very loosely held electrons. The other thing that we learned in Unit 2 is in an alloy is just a mixture of metals. So if you have gold jewelry, it's probably not pure gold. It's probably gold mixed with something else, right? So you can either have substitutional alloys and interstitial alloys. And the important thing there is substitutional is where you take out one of the metal atoms and replace it, you substitute in another metal, and they're about the same size. And then an interstitial alloy is where one metal atom is much bigger than the other. And when one metal atom is much bigger than the other, it creates spaces where the smaller one can kind of get packed in. And you can see that in the pair deck that I'm sharing with you. So just know the difference between substitutional and the other one, which the name escapes me. All right, so when we draw Lewis structures, these are rules, right? And so these are my rules that I use, but whatever rules your teacher taught you, just remember that Lewis structures are very definitely a thing on the AP exam. And we draw Lewis structures for covalent molecules. We really don't do that for ionic or metallic. right? So key things to keep in mind. H always has to be on the end because H only can form one bond. Whoever has the lowest electronegativity goes in the middle, unless it's hydrogen, you can't put that in the middle. The idea is find the total number of valence electrons. So if you don't remember how to do that, then carbon is in group 14. So to find the number of valence electrons, you would take 14 and subtract 10. So carbon has 4 valence electrons. Fluorine is in group 17, minus 10 would be 7 valence electrons. So you give everybody 1 pair of electrons. So everybody gets 1 bond, right? And then anything left over, you put around the outside to give everybody 8. If you have anything left over after that, they go on the central atom. So let's say that you've given out all the electrons that you can. Oh, but wait, there's 2 left over. Instead of going around the outside of the molecule, would go on the center. And then anything in the third period or third row or lower on the periodic table, it can do what we call expand the octet. So it can have not just 8 electrons, it can have 10 or 12 electrons if it really wants to. And remember, that's because it has d orbitals, and that those d orbitals in the third energy level give us a place to put electrons. If you have to, you can form a double bond or triple bond. And just keep in mind the idea of resonance. Resonance is where you've got a double bond on one side, say, and a single bond on the other. And what's important to remember is that it's not static. It's not like the double bond stays on the left-hand side and the single bond stays on the right-hand side. That double bond and single bond can move around because the electrons are constantly moving. So resonance structure is one where we say it could either look like this or it can look like this. Now, when it comes to Vesper, fancy way for what is the shape going to be. Remember, Vesper is all about the electrons don't like each other. And the electrons don't like each other, so they're going to arrange themselves in 3-dimensional space to be as far away from each other as possible. So a chart like this is something that I would either commit to memory, or PHET, P-H-E-T, has a wonderful tool for doing molecular shapes. But as you come into the AP exam, don't forget that, yeah, some of it's math and some of it's doing complicated stuff, but some of it really is actually just drawing a molecule and knowing what its shape is. So knowing what the bond angles are and what the geometries are for different molecules is a good thing to keep in mind that you need to memorize going into the AP exam. All right, so that was just a reminder of those shapes. So now there are 74 of y'all out there. So you get to draw on this slide. So what I want you to do is either pick CO2 or pick CO3 2 negative. I want you to pick one of them, not both of them, just one of them, and draw the Lewis structure for the one you picked. Okay, so go ahead and draw the Lewis structure on Pear Deck, either for CO2 or for CO3 2 negative, whichever one you want. Right, knowing that some of y'all are drawing with computer mice, this will be really interesting. So I'm gonna scroll to the middle this time so that we get to watch people's things. So I'm gonna see, scroll to the middle. I am so proud that so many of y'all showed up, by the way. I'm so happy to see y'all. Thank you for coming out. Several of y'all are still drawing. Here's a squid with a crown. Space alien, not real sure. Okay, a lot of y'all are picking carbon dioxide, which is fine. I told you you could. There's somebody who's doing the carbonate. All right, so far so good. So I am going to point out a couple things when we go over the answers to these, just so you kind of know what was okay and what wasn't okay. All right, so this is two, I just pulled these off of Google Images because I get lazy. So oxide in black, and there's carbonate in blue. Now, notice that the carbonate ion has brackets around it, and the brackets around it are necessary when you're doing a polyatomic ion. So that may be something you want to write down or put down in the back of your head, that when you're doing a polyatomic ion, it gets brackets around it. The reason why there are three of them is that double bond doesn't have to be just in one space. It could be on any of those oxygens. So we draw what we call resonance structures. Now, my carbon dioxide, the CO2, I don't have to draw the electrons. I like to draw them as dots at some 45-degree angle. I totally the way y'all did. That's fine. They also don't have to be linear. I totally could have drawn the Lewis structure as at an angle, like I saw one of y'all do. One of y'all down here had, on the previous slide, when we looked at responses, one of y'all had, in carbonate, you had 3 double bonds. I'm going to see if I can see it. I don't think I'm going to be able to find it. But you had 3 double bonds. And remember, I said that, yes, some things can have 12 electrons, but carbon is not one of those. So keep in mind, the only things that can expand the octet to go beyond 8 are things in the 3rd row and below. So it would not be okay for carbonate to have 2 double bonds, let's say. You just couldn't do it, right? So the double bonds were necessary because that was the only way to give carbon 8. All right, so now that you've drawn the Lewis structure, that was great, right? So this time you get to write out your answer, account for the fact that the carbon-oxygen bond length in carbonate is greater than the carbon-oxygen bond length in CO2. So one more time, here's the structures. And that's the second part of the question. Why is the bond length in CO3 greater than the bond length in CO2? Go ahead and type out what you think the answer would be. By the way, y'all are killing it tonight. You're answering quickly and getting them for the most part right, and that's great. Unit 2 looks good so far. So I'm just going to peek at a couple of the answers real quick. Single bonds are weaker, making them smaller. Carbon dioxide has a bond length of 2, while CO3 has 3 domains. Carbon dioxide has a bond order of 2, which is shorter than carbonate's bond order of 1.33. In carbonate, all the carbon-oxygen bonds are in between the length of a single and a double bond. In CO2, there are 2 double bonds. So, okay, I get that. Scroll down to the bottom edge. I'm seeing lots of bond orders. All right, so lots of good answers. All right, so let me show you what they look like again. So what is the bond between carbon and oxygen and carbon dioxide? It's a double bond. Well, just like somebody said in their answer, single bonds are the longest bonds. Double bonds are shorter, and then triple bonds would be the shortest. So we know single bonds are the longest, double bonds are shorter, and triple bonds are the shortest. So how are you supposed to know what to do with that carbonate down there? Well, when people are saying it's a bond order of 2 and a bond order of 1.33, really what they're saying is, what is the average bond length? So if you have a double and 2 singles, that's a total of 4 bonds, a double and 2 singles. That's a total of 4 bonds shared between 3 oxygens and carbon, right? So 4 bonds split 3 ways means that each bond is not a single, it is not a double, it's more like a bond and a third, right? So when people say it has a bond order of 1.33, that's like saying each bond is kind of like 1 1/3 bonds because of resonance, the idea that that double bond doesn't live in just one place. So whoever said that the double bond is shorter and the carbonate was in between a single and a double bond, you are exactly right. So all those of you who said bond order, that's a great answer too. That's really good thinking. All right, so let's keep the question going, right? So we've done part I and part II. So this is part B. Draw the Lewis structure for either CF4 or SF4. So either one, pick one of them. Draw the Lewis structure for either CF4 or SF4, either one. I got 55 answers. Y'all are doing great. Jumping in and answering questions. This is great. So let me look at a couple of them. Here's an SF4. It's missing some electrons. There's a CF4. It's missing some electrons. Maybe. No, it's not. Never mind. There's a CF4 with what looks like a double bond. There's somebody showing off doing both of them. Ah, okay. If y'all can see the one that I'm showing y'all right now, you can either use dots, or if you want to, you can use just a line, like in the one I'm showing you, to do a lone pair of electrons. AP readers, no matter how you do it, either with dots or lines, will know, oh, that's a lone pair of electrons. There's a cheeseburger. Yes, my hat's a cheeseburger. There's a good SF4. I like that so many of y'all are doing this in various and sundry colors. This is great. I like that someone was doing math, adding things up and stuff like that. So this SF4 is actually not electrons. Wait. This SF4, okay, so the problem, the SF4 I'm showing you, if you look at the fluorine on the left-hand side, the fluorine on the left-hand side has too many electrons. It's got more than 8. All right, so looks like good answers so far. So this is what they wanted the year that this was asked, right? So CF4 is the one on the left, that's fine. And SF4 is the one on the right. So there were enough electrons for SF4 that everybody got 8, right? So everybody got a single bond. And then each fluorine got 6 additional electrons to give it 8. And then there was still a pair of electrons left over. So look at those things real quick, because for the next one, I'm going to ask you to tell me the geometry. So for CF4 and SF4, I'm going to ask you for the geometry of each one. So look at the Lewis structures. And you can just tell me what you think the geometries are. Okay, I got 37 answers so far. So 44 answers so far, that's great. Just what do you think the geometry was? And keep in mind, as you get closer to the AP exam, you may want to write yourself a note now, but make sure you go back over these shapes, because this is an easy point to get in the multiple choice and on the free response. Let's look at a couple of y'all's answers, starting at the bottom. Tetrahedral and trigonal planar, tetrahedral and seesaw, tetrahedral and pyramidal, trigonal pyramidal, bipyramidal, tetrahedral. So I can tell that for some of y'all, it's been a while since you did shapes. So if you're missing shapes, if you're missing geometries, that's okay. Just remember that that's something you definitely need to go back and look at as you cruise into the AP exam in May. All right, so turns out if we go look at them real quick, if you look at, not on the Pear Deck, but if you look at the screen sharing on the Zoom, this is that CF4. So this is a molecule, C in the middle, with all the fluorines arranged around it so that they're as far away from each other as possible. And if we look at the bond angles, they're 109.5 degrees or thereabouts. And that was part of that table that I showed you earlier. So you kind of need to know bond angles in addition to geometry. Now, the only difference between CF4 and SF4 was one more lone pair. So if I add a lone pair, you'll notice that this becomes what I call teeter-totter, because that's what they were called when I was a child, and you guys call seesaw. But that lone pair kind of pushes the fluorines away so that it becomes kind of that seesaw, and you can tell that it's like seesaw, seesaw. So if nothing else, you can pull up that tool even on your phone, and you can play with those shapes, making sure you understand how they get there. All right, so not only are we supposed to know geometry, we are also supposed to know hybridization. So for compound X, the carbon with the arrow on it, what is the geometry and hybridization of just that carbon? So I'm not talking about the whole molecule. I'm talking about just the immediate vicinity, what things are bonded directly to that carbon with the arrow on it. What would be the geometry and hybridization of that carbon with the arrow on it? You can write out your response. And if y'all have not done so already, if you haven't changed your name to school name and then your initials, Mr. Dean is trying to get a count of how many students there are from each school. So I'm going to give y'all a little bit of extra time on this one. So if you could go within the Zoom window and click on the ... or more next to your name under participants, you can change your name to school name and then your initials. Will, Sam Woodfin, we're talking to you. Taylor, Sarah, Ethan, school name, initials. If I was in school, I'd put my school name, but I'm not in school, so sad face. I do say that Mr. Poe is with us tonight. I'm very excited. Probably wearing some kind of Auburn jersey like he always does. All right, so go ahead and lock in and answer the geometry and hybridization. Now on an AP exam, this would be two separate questions. So there'd be like 2 points possible on a free response question. All right, so let's look and see what some of the answers are. Okay, I got trigonal planar or trigonal planar. Lots of trigonal planars. There's a trigonal pyramidal. Trigonal planar and SP1, maybe, I don't know. Okay, we'll go over how to do that again. How to do hybridization. It's very, 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 very simple. All right, so let's do the geometry first. So how many regions of electrons are there around that carbon with the arrow on it? There's 3. So 3 regions of electrons. So the double bond and the 2 single bonds is 3 regions of electrons. We don't have to worry about any of the lone pairs anywhere. We're only worried about the lone pairs on that carbon, if there are any. So how many regions of electrons are there? 3. So how would 3 areas of electrons get as far away from each other as possible? And if you look at the sharing screen that I'm giving y'all, if you had a 2 single bonds and a double bond, that shape would be trigonal planar with a bond angle of 180. In other words, that's how those things would get as far away from each other as possible, right? So trigonal planar. The only way for it to be trigonal pyramidal is if you'd have a lone pair on the carbon, the lone pair on the carbon pushing all the other bonds down. Now, hybridization. Some of y'all, it's either been a while or maybe you never learned or whatever. So hybridization is what orbitals do you mix together? So remember, you got one s orbital and there's 3 p orbitals. And the idea of mixing them is you don't want it to have the energy of an s and the shape of an s, or the energy of a p and the shape of a p. You want to mix them together. So for instance, if it was sp3 hybridized, what that means is you mix together the s orbital and all 3 p orbitals, mixed them all together and created 4 sp3 hybridized orbitals. They're all the same size, they're all the same shape, they all have the same energy of electrons in there. So the idea of hybridization is how can we mix things together? So here's how you do it. You take your hand, you put away all your fingers. You ask yourself two questions. You ask yourself, self, go ahead. Self, good. How many things are stuck to the atom I'm talking about? So how many things are stuck to that carbon? 3. So far, so good. Now, notice I didn't say how many things have a double or triple bond or anything like that. I just said how many things are stuck to it, and we say 3. How many lone pairs are there on that carbon? 0. So add that in. So right now you're holding up 3 fingers, and then you add in 0. That means you need 3 regions of electrons. So you take away 1 finger for the S. So I'm taking away 1 of my fingers for the S. And the number of fingers I'm still holding up, that tells me how many of the p orbitals I need. So I'm holding up 3 fingers. I drop 1 finger for the S. I got 2 fingers up, which means it's sp2 hybridized. Let's do the same thing with the oxygen real quick. The oxygen to the right, the oxygen stuck between the carbon and the hydrogen. How many things is the oxygen stuck to? 2, carbon and hydrogen. How many lone pairs are there on the oxygen? 2 more, right? So add in 2. You should now be holding up 4 fingers. That's 4 regions where electrons go. So you always take away 1 finger for the S. So it's going to be S, and then you're holding up 3 fingers. So it would be sp3 hybridized. Right? Keep in mind just a little bit about pi and sigma bonds. Sigma bonds are the first bonds to form. So a single bond is a sigma bond. A double bond is made up of 1 sigma and 1 pi. So anytime you have additional bonds, like a double or a triple bond, anything over a single bond is going to start adding in pi bonds. So if you look at the molecule on the far left, compound Q, notice that the carbons have a triple bond. So how many things is the carbon on the left stuck to? 2. How many lone pairs does it have? None. So you should be holding up 2 fingers. You always drop 1 finger for the S, and it's going to be sp hybridized. And it would be, that triple bond would consist of 1 sigma and 2 pi bonds. And obviously, if you have a question about that, something you need to go in and ask your teacher, make a note of it, something that you need to study going into the AP exam, because that usually does show up somewhere. All right, so I want you to do 2 things here. Go ahead and draw in the dots where they go for the molecule on the right. And then once you get that molecule on the right, write somewhere on the slide, write down what you think the bond angle is going to be approximately. Let me look at a couple of responses, and I'm probably just going to teach y'all based on those responses. See if anybody's got it so far. And the dots can be either a bond or the dots can be like a lone pair. So I'm seeing some right answers and I'm seeing some wrong answers. So I think I'm going to go just with the one I'm looking at, assuming y'all can see it. So you would have single bonds between all the carbons and the hydrogens. Good so far. You'd have single bonds between the carbon and the oxygen and the hydrogen. You couldn't have a double bond between the carbon and the oxygen because then carbon would have more than 8 electrons and you can't have that. So when you have 2 bonds and 2 lone pairs, then that means that shape, that geometry is going to be bent or angular. And it means that the bond angle is going to be somewhere around 109.5. Now, I'm going to go ahead and argue with you and say that it is not 109.5. It's more like 104. Because 109.5 is going to be when you have just 4 bonds. When you have extra electrons in there, the electrons in lone pairs, when you have lone pairs, they tend to smush the angle a little bit more. So keep in mind, 109.5 is a great answer. I'm not poo-pooing your answer. I'm just saying maybe the better answer would be, because of those lone pairs, every time you add a lone pair instead of a bond, it's going to kind of smush the bond angle a bit more. All right, so this is not anything you're going to do. I just wanted y'all to see this is a question off the old exam, right? So write an equation for the ionization of atomic fluorine. Well, that ionization energy that we talked about last time, they'd want you to write an equation, and they're giving you the ionization energy. Then they want you to explain why the ionization energy of fluorine is greater than oxygen. So exactly what we talked about last week. Predict whether the ionization energy of xenon is greater than, less than, or equal to atomic fluorine. So again, these are periodic trends. And then down low, they're asking you to actually draw those compounds, right? So you can see how they're weaving together unit 1 and unit 2 for you to actually go through, do the unit 1 stuff, and then draw the Lewis structure. And then there were more questions, right? Now, the last thing I wanted to touch on before we left, because I know we're getting close to 8, is formal charge. Formal charge is a way that you can figure out which Lewis structure is better. So y'all did CO2 earlier, and CO2, the correct structure is shown to you on the left. And that's what everybody drew. That's great. But what's wrong with the Lewis structure on the right? You can have a triple bond to the oxygen and a single bond to the other oxygen. You spent all the electrons. No one has more than 8. It's just kind of a wacky way of doing it. So the way you find formal charge is you take all the valence electrons for that atom. So carbon has 4. You take half the number of bonding electrons. So keep in mind, bonding electrons is how many bonds, right? So each bond is 2 electrons. So half of that would be the number of bonds. So in CO2, it has 4 bonds, which is 8 electrons, because each bond is 2. So it would be 4 minus 4 is 0, would be its formal charge. The goal is for everybody to have a formal charge of 0. But if somebody gets to be negative, if somebody has to be positive and somebody has to be negative, then you want the formal charge that's negative to be on the most electronegative element. So if somebody had to be negative, it should be whoever the most electronegative element is, right? So what I want you to do is go ahead and draw on or write your response. What's the formal charge for the HCN and O for the molecule on the left? And what's the formal charge for the H, the C, the N, and the O for the molecule on the right? And trust me, we're almost done. I went way over last time. I'm trying to go just a little bit over this time. So I just have so many interesting things to tell you. All right, so let me just look at a couple of the responses real quick. Zero, -1, +3, 0. 0, 1, +1, 1. Okay, so not too bad. So remember, we rarely talk about what the formal charge on the whole molecule is. We usually talk about what is the formal charge on each atom in the molecule. So I did the math real quick. This is what the formal charge for each element in that compound is. So the reason why nitrogen, the one on the left, is a +1 is because nitrogen has 5 valence electrons, -0 in lone pairs, minus it's got 4 bonds, which is 8 electrons. And so it'd be 5 minus half the number of bonding electrons. So half of 8 is 4. So 5 minus 4 is +1. And the same thing with the molecule on the right. And we come down to the diagram on the left is better because oxygen has a formal charge of -1. And who is the most electronegative out of all those elements? Turns out it's oxygen. So if you don't know your electronegativity yet, you really need to work on that. Mr. Poe, I agree. I teach my students that formal charge is valence electrons minus lines minus dots, but the directions in the A+ College Ready stuff are half the number of bonding electrons. So I don't want to confuse people. Either one works, just don't mix them together. All right, and then to finish up, which one of those molecules is going to have a pyramidal shape? So A, B, C, D, or E, which one is going to be a pyramidal shape? So trigonal or trigonal, pyramidal. All right, let's see what y'all are putting down for answers. A lot of A's, no C's, 1 E. All right, so let's go through what it's not. HBr is just 2 elements, and H2 is just 2 elements. So anything with just 2 elements, the only shape you can make is a line, because 2 points only makes a line. So it can't be C and it can't be E. D is going to look just like water. So if you drew out the Lewis structure for D, H2S, it's going to have 2 lone pairs and 2 bonds to hydrogen, and that would be bent or angular. BH3, when you draw that molecule out, it's going to have 3 single bonds and no lone pairs, and that one's going to actually be trigonal planar. So the only one that's pyramidal at all is A. All right, and this is the one we're going to end on. Based on what we talked about earlier, which one of those do you think has the shortest bond length? And hopefully you've drawn this molecule, or you've drawn many of these molecules. And keep in mind, if you found you struggled with any of these, go and talk to your teacher and say, hey, can you go over formal charge, or I didn't know how to draw this Lewis structure, or make a note on it. And then when you go back to review in April, then you can be like, hey, I need to go back over this. The stuff you're good on, great. The stuff that could use a little bit more work, just make a note of that. That's the reason why we're doing these, is to kind of review stuff. So I got 41 answers so far. A lot of A's. So if you notice, Cl2, Br2, and I2 are all halogens. And if you drew out their Lewis structures, they would all have just single bonds. O2, if you were to draw out O2's Lewis structure, O2 would have a double bond. And then N2 would have a triple bond if you drew that up. And we already said that the single bonds are the longest, double bonds are the second, are shorter, sorry, and then triple bond is the shortest. Okay. Y'all, thank you so much. I will stick around for a minute in case anybody has a question they want. Thank y'all for sticking around. I'm a little bit late, but I appreciate that. I'm gonna go ahead and end that and publish the takeaway.